Okay, so I'm happy to be to this workshop again after several years, and in the last time I presented the same benchmark McCaskill partition functions, because this is like WZ program loop, very interesting because such pattern of loop dependence makes that our very well known approaches cannot extract parallelism. And then I showed the Traco compiler. Now we have the new compiler, and this is one of the first paper which showed the result of this compiler. The main developer of this compiler, DAPT, it's called DAPT, is Maciej Poliwoda. Professor Bielecki is the main author of theory, and I conducted the experimental study. I helped with the theory also, and with the development as my experience. So that's what who has done in this paper. So this is the team approach. Okay, so in this paper, we will compare the efficiency of three compilers, the state of art. Okay, how it's to change. Okay, we compare the three compilers, the very commonly well-known the Pluto compiler, our previous the Traco compiler, and the DAPT compiler, which implements new tiling strategy. It's a space-time tiling strategy. I will say several words about this strategy to explain how it works. And we carried the experimental study with the two new machines with some numbers of cores in processors. Okay, so our target is to extract and to make output code in automatic way. So these tools are source-to-source compiler, Pluto, Traco, and DAPT. This Traco and DAPT are our approaches. I think that Traco is the closed project, and our new research will be concerned to the DAPT compiler, because this new tiling strategy is better and more promising in our future research. And the McCaskill partitions functions, it's the probabilistic RNA secondary structure from the bioinformatics computational biology tasks, intensive dynamic programming problem. Okay, and in the theory, John McCaskill, that was in 1990, showed this method to find the RNA sequence using probabilistic methods, and this method is also used in the MIA method, which was developed, which was proposed in 2010. So it's a little fresh, like for a computational biology theory and algorithm. And the main computational problem in this benchmark is building two dynamic programming tables, Q and QBP, and this is a lot of computation here. This array holds the partitions functions of the subsequences, which form a base pair or zero if base pairing of this RNA sequence is not possible. And the target of this method is to optimize the energy. So E is energy structure, P and R gas constant, RT is a gas constant, and temperature. Okay, and this is the mathematical presentation of the John McCaskill algorithm, and this is it can be presented in recursion. Of course, in parallel computation, we must use the iterative method of algorithm, which was presented in many papers, and I will show you maybe this loop, which of course can be parallel and can be also tiled. Loop dependencies allows us for that and for other related compilers. And RNA sequence is of course combine of chain of nucleotides, which can be alphabet letters from alphabet A, U, G, and C. And the main computations, as you see, is forming these two arrays, and these arrays are two-dimensional. Computations is three-dimensional, so there is a lot of chance to meet again the cell of these arrays and to make these computations cache efficient. Okay, and yes, I said this, and this also this program is difficult because this program loop contains non-uniform data dependencies. So it means that is a class of dynamic programming non-serial polyadic. NPDP in short, it means that there are non-uniform dependencies. So dependencies can have one start and many targets in arrays. This is problematic for compilers, but still the parallel version can be extracted in automatic way. Okay, and we use the Polyhedral model because this loop can be presented in affine form, and automatic tool are able to extract loop dependencies. We transform these dependencies to find new sets, and of course we know where is parallelism. Then we also apply tiling and check that this is correct using the ISL libraries, and using also this library to generate code automatically. And we add only the parallel Pragma OMP parallel for macro to the output code. Okay, so we applied 3 Polyhedral compilers to check that our new tiling strategy is efficient. Maybe I start with the Pluto. Pluto is based on the affine transformation framework, and as I shown in the past, Pluto is able to extract good cache efficiency, but however, it cannot solve to find parallelism in this program loop. And we proposed in the last CANA and not only workshops that Traco can find parallelism. Okay, and this is the dependencies extracted from this program loop of McCaskill. Okay, and this is automatic output generated by Pluto. Pluto is authors are Uday Bungdula and his team. Okay, and as you see, there is no parallelism, so the output is very well tiled, but there is no parallelism. The Pluto is not able; it cannot find it. Okay, and we proposed the Traco. The Traco modify the iteration space, moving dependencies, moving statements, to the later tiles, so the output tiles are modified. Then the tiles can be executed in parallel. but the shapes made that the code is the styling is a little worse than tiling of Pluto, but it's parallel. So if we execute this on many threads, and the times in total will be better. And okay, and the theory to find these dependent statements in tiles, we're using transitive closure to find all transitive paths that we moved. As you can see, this yellow statement, because we cannot have in tiles the statement which is the target of dependence in the tile which is in future, because it's we cannot corner dependencies then, so we must modify the shape. And that was our approach, very well documented and made with a lot of program loops, but this still some miss. We change the shape. So, for example, we must looking for good tile sizes. We must a lot of make experiments to adjust the output code to the special target machines. And we think that we can correct by other idea. Yes, this is also the output Traco compiler. As you can see, the second program loop is parallel, but the tiles we have different tiles with different amount of statements. Okay, so it's the grains are in different sizes. Besides, we shown in past also that the Pluto, for example, is not able to tile all program loops like in the Nusinov algorithm, and the Traco is possible, but the code is irregular tiles, and this is what we wanted to correct. Okay. And the adapt compiler, this is the new tiling strategy which we invented about 3-4 years ago. So that was some time to implement this in practice. And the idea is that this is space-time tiling. So we freeze tiles which has some dependencies, and we make some space of tiles, freeze them to the moment that they can be executed, that all sources of these dependencies in this tile have been executed earlier. So this is the space-time tiling. The result is that we make the code more regular. But the good sides of the Traco is still that we are able to extract more regular code and with the parallelism in the McCaskill algorithm. Okay, so as you can see, the code is much shorter. The tiles are more regular, so that's why that much more shorter, because in Traco there are different shapes and we have a lot of if statements, and this code is also better in time, which we shown in our experimental study. We chose to this target machines, two machines. One machine is it was a great machine because it was with 9060 threads, machine threads. So in the main board there was two Intel Xeon Platinums. The machines was accessed to thanks to the Częstochowa University. They had access from the Intel corporations, but only for the moment. But I made these experiments, and we have also the AMD EPIC in the opposite of the another processors. This processor has 32 cores, hyper-threading, so we had 64 machine threads, CPU threads, yes. And in the Intel Xeon Platinums, we could use the Intel C compiler with the AMD EPIC that was only a G++. So that was our environment, and we achieved very good times for the Intel machines. So it was very good scalable, and the Traco was similar because the Traco has worse tiling. For the AMD EPIC, the results were much better than Traco, but closer. I think that's the result is that we chose the Intel C compiler, and maybe that results were better than in the AMD EPIC 7542 processor case. Okay, and in conclusion, so this is one of the first papers that present that the new tiling strategy is very interesting and is our future research. And the space-time tiling is not finished, that is only proposed. It can be proved in many places. For example, we didn't check which good tile sizes could be the best, but all tiles are regular. We have parallelism, so the main idea of this paper was done. And the future work is to apply the NPDB benchmark suite that McCaskill is one of this kernel of this benchmark. We will present this benchmark in the Gdańsk next week. I hope to meet also Professor Stipczyński from the Lublin on his workshop, and then because the paper only contains experiments with Pluto and Traco, now we make experiments with DAPT, and I think that will be some output research of DAPT and this new benchmark suite in some journal in the closest future. And that's our future research study, and thank you very much for your attention. Thank you very much.
Thank you very much. And we will gladly hear any questions. So I would ask you for one clarification because maybe I missed this. Who is author of DAPT?
DAPT, yes, this is the acronyms of letters of Maciej Poliwoda, and this is some words of transformation, affine, processing D. I forgot what is a D, but in the main that is a space-time tiling, and the author is Maciej Poliwoda. So sorry, but I forgot these words. I think that in paper is explained.
Okay. Thank you very much, and it's we have seen that the DAPT behaves very well in comparison to Pluto and Traco. If I
yes.
If I
okay.
If I have seen well, okay, yes. So I observe the development of Traco, and I have questions about other algorithms, other codes.
Yes, because we now do experiments study, and McCaskill is of course some spectacular good speed up. So I chose this to present to this workshop. but also it's very good cache efficiency for the Nusinov algorithm, for the Smith-Waterman algorithm. The word situations, maybe another words, we didn't check very well. It's better word situations is in case of for double nested program loops, because there the cache efficiency, the lack of the Pluto, it's corrected by the arrays which cannot tile Pluto. The loops are have not many iterations in opposite of the outer loops. So this is in this benchmark, the 4 double nested program loops, like for example Smith-Waterman, but not for 2 but for 3 sequences, we have 4 loops, and there is situations not black and white. So this is it needs more deeper experimental study to, because we cannot say that our method is better. Maybe for this one machine, but not especially for another machine. It's dependent. There are a lot of some variables in this experimental study.
Okay. Is that source accessible?
Yes, I think that is in paper, but
maybe I didn't notice.
Okay. So we correct this, but the target is idea is the same like in Traco. We show everything, and everybody can study, track, and improve. So we do not close the sources because it's some license very free.
Very good. Okay. So thank you very much.